Sorry, folks, I have been called into a meeting, and so I will have to miss Tuesday's class. So what I'm going to do instead is just go through section 5.2, my lecture notes with you, so you can kind of see what I would have lectured on in class. So here we go. And maybe I could actually do that. All right, so first thing you should know, in section 5.2, definite integral is what the section is titled. We already talked about the summation properties here, so I'm not going to bother with them. We've also talked about these summation properties. They're in your text. You are responsible for knowing, and maybe I should put this on here. So insert, I'm going to put insert screen clipping so I can talk about it here. There we are. Okay, oof, man, that is a big old screen clipping. Okay, so, again, sorry, this is not going to be very polished because I'm not trying to make it polished. But anyway, you're responsible for knowing those on an exam. However, yeah, no, there's no however. You're responsible for knowing those on an exam. Okay, you should have known at least that guy right there from pre-calculus and this guy right here from pre-calculus. The square, when I teach pre-calculus, I often give my students the square as a formula. It's really the only oddball formula. You should be able to remember that at this point. Okay, going back to my lecture notes. Now, definite integrals is where we kind of left off in the lecture. You can kind of ignore this. I'm just going to write down what a definite integral is. And let me resize this, put this view on 100% here, and move up. So the definite integral from a to b of a function of x dx, well, that's just the area. We can kind of think of it this, well, actually, maybe I shouldn't say that yet. It is defined to be the limit as n goes to infinity of the Riemann sum, I equals 1 to n of f of x sub I star delta x, right? And this is where delta x is equal to b minus a over n, right? The distance between the beginning and end point of the interval, and n is the number of slices, and then x sub I is equal to a plus I times delta x, and x sub I star, which I don't really make a big deal of in class, but x sub I star is a point somewhere in x sub I minus 1 to x sub I, that closed interval. If you're using the right-hand point method, so let me go ahead and change the color here. If you're using right-hand point, then that's what you're going to be using, x sub I. If you're using a left-hand point method, or left endpoint method, you're going to use x sub I minus 1. If you're doing a midpoint method, well, then you're going to average these two. So the midpoint method just takes x sub I minus 1, adds it to x sub I, and then you divide by 2 because you're averaging them. All right? So everything we learned in 5.1 can now be used to approximate values of integrals, of definite integrals. So if you go through, this is just my lecture notes, and you can see introductory examples. So what I'm going to go ahead and do is actually steal my introductory examples, and also I'm going to shrink this down because I think that that was the issue when I tried to insert that screen clipping before. So I have this little note on here as well. So express this limit, n goes to infinity, I equals 1 to n, e to the x sub I plus tan inverse of x sub I minus 3x sub I, and delta x. It's very, very important that delta x on the back end here. Express that as a definite integral on the interval -1 to 15, but do not evaluate. Okay, so from -1 to 15, this is actually a very easy question to answer because this, as we've written up here, that limit notation is defined to be the integral of f dx from a to b. So that limit notation that you read right there is defined to be the integral of the function that we have in here without the x sub i's, just e to the x plus tan inverse of x minus 3x squared. And then that delta x, because we're taking these slices infinitely thin, because the limits go into infinity, we call that a dx. And then we also get to say that x is going from a -1 to 15. That's all we have to do. Do not evaluate this, is what I tell you, so don't bother evaluating this. All right, so let me scroll down a little bit. Let's throw on here the next introductory example. Let me go ahead and insert that. Tap down here first, and then insert that. Again, I apologize for the last-minute canceling of class. All right. Introductory example, express the integral as a limit of Riemann sums and do not evaluate. Now, this is actually the harder way to go. Remember, this is supposed to be defined to be the limit as n goes to infinity of the summation I equals 1 to n of f of x sub I. I'm just going to call it f of x sub I, not f of x sub I star, times delta x. Now, the function in this case is going to be x minus 4 natural log of x. So all I need to do is actually just call the x sub I minus 4 natural log of x sub I. And instead of dx, I'll have a delta x. And you might think, great, we're done. And maybe some instructors will allow you to stop there, but I will not. And here's the reason why. I think that you can go a little bit further here. So let me write this as x sub I minus 4 natural log of x sub I. And then that is times a delta x. But they specifically said x is going from 1 to 10. So actually, I can find out what delta x is, and I can find out what x sub I is. Remember, delta x is always defined for us to be b minus a over n. Remember, b is the upper limit, a is the lower limit. So this is going to be 10 minus 1 over n, or in other words, 9 over n. So that delta x that I have written right here, I can erase that and call that a 9 over n. But not only that, we also know that x sub I is just a plus I times delta x. Well, again, a is this lower limit, which is 1, plus I, and we just computed delta x to be 9 over n. So really, all those x sub i's that you see in there can be actually written a little bit, well, it's not cleaner, honestly, but it can be written differently. I equals 1 to n of, instead of x sub I can call it 1 plus 9i over n minus 4 the natural log of, again, 1 plus 9i over n. And delta x is just 9 over n. Now, you really can't do very much from here because it's within a sum and all this other stuff. You could technically take out n's, but because that natural log, remember our theorems that we have up here, you can trade out, let me go ahead and shrink that down so we can see it. You can trade out any sum of I squared or any sum of I cubed or any sum of I, but I don't see a sum of a natural log there. And so because of that, let me go ahead and get back to my normal view. Because of that, this summation right here of this natural log is stuck. So I'm not going to bother simplifying any further. I'm just going to stop there. Okay, so that's my kind of two introductory examples. And now we go into, as I recall, the properties of integrals, definite integrals. So we're going to describe each of these. Let me go ahead and make some room here. I'll tap right there. And oh, no, I guess I'm not going into properties. Sorry, let me go ahead and copy and paste this theorem. As I said, it was as I recalled, but obviously I recalled incorrectly. So let's go ahead and do this. I'll copy and paste. All right. Left endpoints, right endpoints, and midpoints. So a definite integral can be found using any point on the given interval. However, we often use left, right, or midpoints. And actually, I talked about that already. So, but there's the formula, or the formulas for the x sub I stars there. And then, as I just saw, I have a couple examples here. And I tell myself, this is how my notes are. I tell myself when to use technology. So let me go ahead and copy both those. This is all still section 5.2. I just didn't have the second page of my notes, I guess, on the other day when I was lecturing in class. So I thought, oh, I don't have much else to lecture on. But actually I do. So let's do this first example. Use the midpoint rule with n equals 4 to approximate. We're not actually finding the value of it. We're approximating what this integral is. The integral from 0 to pi over 2 of cosine to the 4th power of x and then dx. So what I'm going to do is say this is approximately, again, midpoint rule with n equals 4. So I'm going to sum up four things. I equals 1 to 4 of f of x sub I star times delta x. Again, this integral is equal to the limit as that upper value goes to infinity, but because we're not letting that go to infinity, then I'm not going to be able to get the exact value. I'm only going to get an approximation here. Let's go ahead and compute what delta x is. Again, you get sick of this, but it is something we have to remember. Delta x is b minus a over n. In this case, n is 4. So we have delta x is pi over 8. And then x sub I is a plus, well, I don't need to write that. It's a, which is 0, plus I times delta x, which is just pi over 8 times I. Now, because I'm using the midpoint rule, that x sub I star, oh, actually, I have it written right up here, is this business, right? It's the average of x sub I minus 1 and x sub I. So if I were to do this, and I do think I have a calculator around here somewhere, if I were to do this using a calculator, what I would probably do, honestly, is write down a table of values. So let me go ahead and at least clean this summation up a little bit. I equals 1 to 4, and this is going to be f of x sub I minus 1 plus f of x sub I minus 1 plus x sub I, all divided by 2. That's the midpoint. And then we were just told that we just computed that delta x is pi over 8. So times pi over 8. Now you could go through and figure out what x sub I minus 1 plus x sub I are. You totally could do that for each of them. But I think that's kind of a pain. So again, what I generally do is I build a table of values. I'm going to build it up above here. And so I look at x sub 0, x sub, I'll leave a little space in there actually, x sub 1, x sub 2, x sub 3, and x sub 4. X sub 0 is the beginning x value on this interval. That is just, that is just 0. I don't know why it jumped over, but is just that 0 there. So x sub 0 is 0. X sub 1, I'm left-handed, so by the way, my hand keeps hitting the screen and making it jump around. That's the problem with being left-handed. X sub 1 is just delta x away. All these points on the x-axis are stepped away from each other by delta x. So my delta x here is, let me make this supersized. And my delta x, what is going on? Hold on a second. There we go. I just moved my screen. That's what it was. My delta x is pi over 8. So if I started 0, I would go by a step of pi over 8 to get to the next x value. And I'd go by another pi over 8 to get to the next x value. And I'd go by another pi over 8. And so on and so forth. Now you see, I'm not actually simplifying these. I only do that at the very end. I just go, what's 4 pi over 8? Well, that's pi over 2. And that's exactly where I should be ending, at pi over 2. Now the question is, what are the midpoints? I'm going to use a different ink for this just to showcase. What's between 0 and pi over 8? Well, it's just half of pi over 8. That's pi over 16. And believe it or not, when we go to the next midpoint, we're just going to add, again, our step size, which is a pi over 8. Well, the denominator is a 16, so I'm going to call that 2 pi over 16, just to make the math easy. So this is how I generally compute midpoints, is I go ahead and write down the list of the points, and then I start at the first midpoint, which is usually pretty easy. Just average up 0 and pi over 8, and then I add the step size, which is 2 pi over 16, so I get to 3 pi over 16. Add another 2 pi over 16 to get to 5 pi over 16. Add another 2 pi over 16 to get to 7 pi over 16. And those are my midpoints. So I don't actually have to use any other kind of formula with this. I could just say, okay, great. This summation is the same thing as f evaluated at pi over 16. I'm going to group this all up because it's all going to be multiplied by pi over 8. So, darn it, left hand, get out of the way. Plus f of 3 pi over 16 plus f of 5 pi over 16 plus f of 7 pi over 16. And again, this is all multiplied by pi over 8. And so what I would do is I'd look at my function's cosine to the fourth, and I would evaluate that at each of these. Plus cos to the fourth, right? At the next one, so I'd grab a calculator and do that. Multiply by pi over 8 in the end. Okay, so that's how you would do that approximation. You get some numerical approximation to that. All right, so that's that example, and you'll be asked to do that in the homework. I think it's fairly realistic to expect that you can do that. Now we're going to go back into the next example, which says, consider the function f of x equals, it's a parabola, right? F of x equals x squared minus 4x plus 4. Graph this function. Well, okay, that's actually not too terrible. If I look at f of x is equal to x squared minus 4x plus 4, it's the same thing as saying I'm looking at x minus 2 quantities squared, right? So that's just a parabola shifted to the right 2 units. I go ahead and cheat a little bit and throw down an axis, shift my parabola 2 units, and it looks something like this. And so you graph this function, discuss this. Now this is me mentioning to myself what I want to talk to you guys about. Discuss this as a difference of areas. I have no clue what I would mean there. So I'm going to wait until I go to part B. So we've graphed the function, and then it says estimate the value of the integral from 1 to 8. The integral from 1 to 8 of f of x dx. Well, this is 1 right here. Here's 2. Here's 3, and so on and so forth. And 8, I mean, that's going to be way over here. Way far over there. But they want us to take 7 slices to do this. Okay, and right endpoints, by the way, r sub 7. So I'm going to approximate this using right endpoints and 7 slices. Well, if you think about that, if you're going from 1 to 8, your delta x is going to be 8 minus 1 over n, which is 7 here. That's 7 over 7, or 1. So our delta x is these actual step sizes that I'm writing in here. You know, the distance between 1 and 2, the distance between 2 and 3, the distance between 3 and 4. And we want to approximate the area underneath this curve using the right endpoints. Well, if you look at this first interval from 1 to 2, the right endpoint is at that height. So the very first rectangle is that rectangle. It's not much of a rectangle, is it? And then the next, so that's first area, the second area is right here. Second area, the right endpoint is right here. So I'm going to approximate the area using this. The third area is right here. And using the right endpoint, you get this. And you get the idea, right? This is going to be a terrible over approximation, but let's go ahead and do it. Oh, and I tell myself to use technology. So let me pause this, And then I will go ahead and plug in, or maybe I could just do this right now. I'll just plug in my thing here. And let me pause it anyway. All right. So let's see. I know that delta, I'm just typing it in, delta underscore x, that's just equal to b minus a, which is 8 minus 1, over n. Now, there's no real reason for me to type that in there, but I'm doing it. A is equal to 1, b is equal to 8, and I know that x sub I, well, actually, I'll just write it in here. I versus x sub I, and f of x sub I. I'll need all those, right? You need to know what the function is at x sub I and so on and so forth. And I'll start at I equals 0 and go all the way down. Actually, because I don't have a mouse hooked up, I actually have to type these in. Oh, no, I don't. I'm thinking about it. I can do this and drag down. I think I can drag down. There we go. All right. And x sub I is going to equal a, and that a is never going to move, so I'm going to put an F4 on that. if I can figure out how to do that. Function F4. There we go. And let's see, plus I, and that I will change, times delta x. Again, that delta x, I'm going to anchor. So I'm going to say function F4. And then click there, oops, and double click the bottom right hand corner just to do that. So those are my x sub i's. Oh, my a is not 1. My a is 0. I was wondering what's going on. Okay. Let's see. No, my a is not 0. Let me go back to the problem here. A is 1. It goes to 8. So b is 8. A is 1. B is 8. Right? And let me pause for a moment. I don't need to pause. It's this last line here is not needed because we're doing 7 slices, not 8 slices. Sorry about that. Let me delete that. Anyhow, all right. And then I just need the function values at these points. So this is going to equal, it was x squared. So this guy squared minus 4x. Again, sorry about that. And then plus 4. And I'll go ahead and double click the right hand corner to move that down. Okay. And now all I need to do is just, if I'm using right endpoints, I'm going to start with this guy, x sub 1, and go all the way to x sub 7. I'll write that down in a moment, but it does actually add up f of x sub 1 to f of x sub 7. So let me go ahead and say this equals the sum of, and I'll start here, and all the way down to there, close it out. And then that's the sum of the function values, but really we need to multiply that by delta x. Multiply that by delta x. And delta x is just 1, so it's still 91. So now let me go back. I'm going to flip this over so you might hear a lot of noise. Sorry. Let me go back to the thing here. So this is equal to 91. That's the area underneath the curve. And again, I was going to explain something. I forgot what it was. Oh, yeah, it was right-hand point. So if you're using right endpoints, then you're really evaluating, this is x sub 0, this is x sub 1, x sub 2, x sub 3. So the right endpoints start at x sub 1. That's why when I was adding these up, I was really only concerned with x sub 1 and then x sub 2 and so on and so forth. Anyhow, that's kind of another technology example. We had one in class, but it's good to see one here as well. All right. Now, let me go ahead and capture this and bring this to this screen. And I think I have some room here. Insert, screen clipping, couple theorems in a row. Actually, I'll just do one at a time here. All right, first one, integrability, I can't say that word, implies the limit of a Riemann sum. Basically what that means is that if somebody says a function's integrable, right, on an interval, so that you can take the integral of it on an interval, that means it is actually the limit of a Riemann sum. So when they say this exists, you know this limit exists too. Okay? That's nothing really huge. It's just kind of an important point. So if somebody tells you I know this integral exists, then you know its limit version exists. Just like, by the way, when we learned about derivatives, right? If I told you f prime of x exists, then you know the limit as h goes to 0 of f of x plus h minus f of x all over h, you know that limit exists. So just like the derivative is actually a limit, an integral is a limit. All right, that's all I wanted to mention there. And let me go ahead and do a screenshot again for the next theorem. Continuity or, let me pause this while this fixes itself. I'm not sure what happened. But anyway, continuity or finite discontinuity implies integrability. So if you have a continuous function, or if it only has a finite number of jump discontinuities, that's actually kind of important in differential equations, a finite number of jump discontinuities, then you know that it has an integral that you can evaluate, or it has an integral. You might not be able to evaluate it, but it has an integral. And a way you can visualize that is if I give you a continuous function, you can find the area underneath it. If I give you a discontinuous function, but it has jump discontinuities, like that, okay, you can still find the area underneath it, right? I'm just shading them in, but you can find that area, okay? As long as it has a finite number of jump discontinuities. It doesn't allow for infinite discontinuities, just jumps, okay? All right, and I'm not going to do the next example in line because it's just a tabular problem. I want to get these properties. These are the most important part of this section. And I should probably pause this because the fact that this OneNote just broke on me makes me think it's going to break on me again. But let me just see. There we are. Okay, properties of integrals. The very first property here is one of the most useful properties for integrals. The integral from b to a of f of x is the same thing as the opposite of the integral from a to b. Now that is not easy to understand. There's many of these that are easy to understand. In fact, let's start with the easy to understand ones. I'll call this 1, I'll call this 2, and 3, and 4, 5, 6, 7, and 8. All right. Number 2. If you're going to add up the area underneath f of x, and you start at x equals a, and you end at x equals a, you have added nothing. So therefore, 0. That is fairly understandable, right? Another way you can think about that is that this is supposed to be the limit as n goes to infinity of the summation I equals 1 to n of f of x sub I times delta x. But delta x is the difference between the top and the bottom limits divided by n. The difference between the top and bottom is 0. So this delta x is actually 0. So you just have 0 times a summation, and that is 0. You're done. Okay. The number 3 is also somewhat easy to understand if you draw a picture. It says if you've got a constant curve, and let me go ahead and over on the right-hand side, I'm going to write number 3 right here. If you have a constant curve, so here's my xy axis, here's x, and here's y. And let's pretend that we have a line y equals 5. And you want to find the area underneath it from A to B. because that's exactly what number 3 is saying. I'm finding the area underneath this curve C, which is a constant, from A to B. Well, that's the same thing as finding the area of this rectangle. That's length times height. The length there is B minus A. The height is the 5. And in general, if that wasn't a 5 and instead it was just a constant C, then you would get C times B minus A, which is exactly what 3 is. So we've discussed 2 and 3. Those are pretty easy to understand. 4 is even easier to understand. If you want to find the area underneath the curves F plus G or F minus G from A to B, you can find the area underneath the curve F first, and then add the area underneath the curve G. So let's actually talk about that. This is the same thing as saying, actually, black is fine. Here's my curve F from A to B. And here's my curve G from A to B. If I want to find the sum of the areas, I can find the area underneath F first and add to that the area underneath G. That's exactly what this is saying. If I want to find the sum of the areas, I can find the area underneath F first and then find the area underneath G and add them up. Or same thing with the differences. Number 5 is actually incredibly easy to understand. Probably backwards, it's easier. If I'm going from A to B, and there's some number C somewhere in there, and I'm finding the area from A to B, it's the same thing as going from A to C and then C to B. A to C and then C to B. So you can break up integrals if you want to. So 2, 3, 4, and 5 are pretty easy to kind of grasp. I'm going to pause so I can take a drink. Actually, 6 should not be too terrible either. That's supposed to say if f of x is positive. So if f of x is positive or non-negative for all x on the interval, then the area underneath f should also be positive, right? So if you could write that down, if f is positive, then area under f is positive, right? If it's above the x-axis, then you have a positive area. 7, if you got a function above another function, this is actually easier to see than it is to say. So I'll use black again. So, oops, I don't know how I did that. That was magic. And yet again, I don't know what is going on with my pen, but that's all right. I'll just draw it. Okay, so if you have a function, let's say f here. That's f. And it's always above a function g. There's g. Notice f is always above g. What does that imply? It implies the area underneath f from A to B is always above the area underneath g from A to B. That should make sense. That's all that's saying. So again, 2, 3, 4, 5, 6, and 7 should be very understandable. The two that are kind of oddballs are 1 and 8, the outer ones. Let's talk about 1. Suppose you have an integral from b to a of f of x dx. Well, that means that here's a and here's b. It means you're going the wrong direction. It's really what it means, right? Remember, that's the limit as n goes to infinity of the summation I equals 1 to n of f of x sub I delta x. Well, here's the deal. Your delta x's here are going like this. They're going the wrong direction. because you're going from B to A. So if you want to instead go the other direction, you'll have to put a negative there, right? If you want to make those delta x's go in the positive direction, like this, you're going to have to reverse or put an opposite on their direction sign. And so if you do that, you're going to go from A to B. That's kind of the idea behind it. This is actually an incredibly important theorem because it's very often the case that you're integrating from, like, let's say 10 to 1 of sine of x dx, and you just don't like to see it like that. You like it written the other way around, so you can say, listen, I can flip the limits if I throw a negative out front. So all we're pretty much doing with this material is just getting used to manipulating the forms of the integrals. Definite integrals, that is. And let's see, the very last one here, number 8. This is, again, another one of those that it's best seen via a graph. And this one, if it graphs upside down, is perfectly fine. I'm okay with it. So let's suppose that you have a function. Let's say it goes from A to B. And let's keep it all above the x-axis, okay? Let's say it does something like this. So on the interval A to B, it has a lowest value. This lowest value here, right? The lowest y value. That's going to be called y equals little m. It also has a highest y value. It looks to be this guy right here, so I'll just do that. It has that highest y value. That's y equals capital M. Now think about the area underneath the black curve, which is f, by the way, from A to B. That area from A to B underneath that black curve f of x dx. Well, if you take a look at it, it's definitely greater than the area here that I'm highlighting, right? It's greater than that area, and that's just a rectangle. So it's definitely greater than b minus a times the height little m. So if you happen to know the lowest point on the curve f, you can say, well, now the area from A to B is definitely bigger than b minus a over little m. And by the way, it is also true that the area underneath this curve f is less than the area underneath this big, tall y value, right? All that area that I'm highlighting in green, definitely more area than the area underneath f. And that area in green is, again, a rectangle. It has height, capital M, and width, b minus a. So if you happen to know the maximum value and the minimum value for a function on an interval, you can get a boundary for what the value of the integral is going to be. You won't get an exact value, obviously. These will just be bounds. Again, I'm going to pause for a moment. So let's go ahead and evaluate some integrals by interpreting terms of areas. Very, very common question, right? Or maybe you don't know that, but it is very common to be asked to interpret the value or to find the value of an integral, definite integral, by first looking at areas. So let's take a look at the integral from 0 to 2 pi of sine of x dx. Now remember, that's the area underneath the curve sine of x from 0 to 2 pi. I don't need to do anything fancy here. I'm just going to draw out the sine curve from 0 to 2 pi, and I'm just quickly sketching it, so you'll have to forgive any bad curve sketching. But you can see that area is symmetric. I have a very positive area, right? All that area is positive y values times widths. And then I have a very negative area. These are all negative y values times widths. Negative y values will subtract areas away. So you have a positive area and you have its symmetric negative area. So if this was an area, let's say, of 5, then that's an area of -5. And so you have 5 plus -5, or in other words, you have 0 in the end. By the way, that area is not 5. I'm just writing that as an example. So that is a great way to use a graph to help you evaluate the value, to figure out the value of a definite integral. Another way, and we did this in class, but I'll just write it here again, -3 to 0, we did something like this, I should say. The integral from -3 to 0 of 1 plus the square root of 9 minus x squared dx. Believe it or not, in Calc 2, a lot of students struggle with this type of problem. If you just know how to graph, then this problem is very easy for you. If you know that, well, one, I'm going to use a property of integrals. I'm going to break this into two integrals. By the way, don't forget those dx's on there. It's often the case that people do. And then what I'm going to do is look at these geometrically. So the graph of y equals 1. Well, the graph of y equals 1 is this, is y equals 1, right? And I'm going from -3 all the way up to 0. So I just want to know what that area is. Well, the area between -3 and 0 there is, well, the length is 3, the height is 1, it's 3 times 1. And then let's look at y equals the square root of 9 minus x squared. Well, it's positive because it's y equals the positive square root. So I'm only looking at the upper half of something. And if you square both sides of it, you'll see you're looking at y squared is equal to 9 minus x squared, or in other words, x squared plus y squared is equal to 9. It's the upper half of a circle of radius 3. But I only want the area of the upper half of that circle from -3 to 0. So that area right there, from -3 to 0. Well, that's just 1/4 of a circle. And I know that 1/4 of a circle is 1/4 pi r squared. The radius here is 3, though, so 3 squared. So in the end, the value of that integral is going to be 3 plus 9/4 pi. So that is using graphing to help you kind of evaluate a definite integral. Remember, definite integrals go from a lower limit to an upper limit. Now, you often cannot graph. I mean, there's just too many crazy functions you're going to integrate that graphing's not going to really help you that often. But when it can help you, it's pretty great. Now, let me see what I have coming up here next. Oh, yeah, this is great. So let me go ahead and throw this onto here. Do this. Come on, click on there. Insert. Screen clipping. And grab this guy. Such a good question. Given that we are told, so somebody just comes in the room and they say, guess what? The integral from 1 to 3 of e to the x, that's dx. They tell us that's just e to the third minus e to the first. They don't bother telling us why. They just say that it is. And then they come along and they say, so because you know that, I now know you can evaluate the integral from 1 to 3 of 2 e to the x minus 1. And you don't have to freak out because you can use properties of integrals here. I can break this into the sum of two integrals. So integral of 2 e to the x from 1 to 3 dx. And then minus the integral of 1 from 1 to 3 dx. And of course, that 2 can be factored out of that first integral. That's 2 times the integral from 1 to 3 e to the x dx. Minus, and we just did that one right there, or one similar to it. You have a width of 3 minus 1, or 2 times the height of 1, so it's just an integral. Area of 2. 3 minus 1, which is 2 times the height of 1. And we were told what the integral from 1 to 3 of e to the x is. It's going to be e to the third minus e to the first. So let's go ahead and plug that in. E to the third minus e minus 2. And now you can go ahead and either factor a 2 out of everything and get e to the third minus e minus 1, or you could have multiply 2 against everything, whichever. But that's the area underneath that curve, 2e to the x minus 1 from 1 to 3. Now I'm going to pause so I can take a drink. We're quickly approaching the end of the lecture here. I'll write the following as a single integral. Let's see. I have going from x equals a negative 4 to 2, and then 2 to 3, but I'm losing the area underneath the curve from negative 4 to negative 1. Now, let me illustrate this. I have some curve, and we're adding up all the area underneath that curve from negative 4 to 2. So that's the very first integral. It's this area right here. And then we're also adding to that the area from 2 to 3. But then we're taking away the area from negative 4 to negative 1. Here's negative 1. So what I'm going to do is take away the area from negative 4 to negative 1. And so what I'm left with is the area from negative 1 to 3 altogether. So that visualization there is a great way to do it. Or you could say, oh, I'm going from negative 4 to 2 and then 2 to 3, so that's negative 4 to 3. But I'm losing negative 4 to negative 1, so therefore I'm left with an integral from negative 1 to 3 f of x dx. Okay, now let me see what I have coming up next. Now I actually changed the wording on this because I just want to make it more interesting. Find a bound for the integral, the area underneath the curve, from negative 1 to 1 of 1 over x squared plus 1. Okay. So first thing I'm going to do is graph this. When they say bound that means to me I need to find its minimum and its maximum. So if I plug in x equals 0, I get an output of 1. And now, by the way, if f of x is equal to 1 over x squared plus 1, I'm actually going to use a little bit of our calculus that we've had before. I'm going to go ahead and try to graph this. The domain is all real numbers, right? The intercepts, when x is 0, we just found as 1. And then there are actually no x-intercepts because the numerator is never 0. Symmetry, let's see, f of negative x is actually the same as f of x, so it's even. Let me move this over to the right here, even. Let's see, what else? What other things do we want? Oh, horizontal asymptotes. So as the limit as x goes to infinity, I don't have to worry about negative infinity because it's even. As x goes to infinity, well, that fraction goes to 0. So I happen to know the horizontal asymptote. It tends to 0 here. Let's see. There's no vertical asymptotes because the domain's all real numbers. F prime of x is going to equal derivative of the top is 0 minus the top times the derivative of the bottom, all over that denominator squared. And as long as we're only, since we're dealing with the fact that it's even, as long as x is positive, this is negative. So we know that it's decreasing. We know it's going to be decreasing in the positive x direction. And then also f double prime of x, derivative of the top is negative 2 times the bottom, x squared plus 1 squared, minus the top times the derivative of the bottom, 2x squared plus 1 times 2x, all over that denominator squared. And let's see, both, there's a lot of stuff you can factor out here. Both terms in the numerator have a 2 and an x squared plus 1, and the x squared plus 1 will cancel with 1 downstairs. So I'll have a 2 times, and then downstairs I'll have an x squared plus 1 cubed. And let's see, I factored out a 2, so I'm left with a negative. I've only factored out one of the powers of x squared plus 1. Plus, let's see, I have 2 times 2. I've already moved one of the 2's out, so I have plus 4x squared. Let me just double check. 4x squared, yes. And let's see, so that numerator is going to be 2 times 3x squared minus 1. And that's over x squared plus 1. Cube, that denominator is always positive. Let me draw a number line for f double prime. We're going to start at 0 because, again, you don't, it's even. So behavior on one side is the same as the behavior on the other. And that f double prime is 0 at 1 over root 3. So you can plug in any number less than 1 over root 3 into the second derivative. I'm going to put in 1/10 because that's less than 1 over root 3. If you do 1/10, you get 0.03 minus 1, which is negative. Over positive, it's going to be negative or concave down. And if you plug in any number greater than 1 over root 3, like a 1, you get positive. So it's concave up. So I know it's decreasing. Initially, it's concave down, and then it switches at 1 over root 3 to being concave up. And I have to turn my computer to do this, so give me a moment while I do this. Come on. I'm left-handed, and this is just being mean to me. There we go. All right. So this is what the curve looks like, and then it's symmetric about the y-axis, so I know it looks like that. Like kind of like the bell curve in a way. Okay. All right. And I happen to know the minimum value it's going to have is 0. The maximum value it's going to have is whatever this is, which is 1. So I happen to know that the integral, the area underneath the curve from -1 to 1 of 1 over x squared plus 1 dx, well, that is between the minimum, 0 times b minus a, and the maximum, 1 times b minus a. Well, that means that this integral is between 0 and that's going to be 2 times 1 or 2, between 0 and 2. And that, by the way, is just using, if I scroll up quite a ways, this guy, I'll highlight it. Okay. Now there's quite a bit of other things you're going to be using. Well, no, actually, it's pretty much just everything I talked about. But there's a lot more to integration. But luckily, Section 5.2 is just kind of building the definite integral stuff. Section 5.3, which we will do on Thursday because my meeting is only on Tuesday. Section 5.3, you'll get a little extra in there, a little more of this. But it'll be the fundamental theorem of calculus on Thursday. All right, I'll see you then.